let's start, and then if other people join, that's fine. Um, my name is Mithra Sankrithi. I appreciate the chance to share some thoughts and some of my experiences. Maybe I'll start just with a real quick background of my own education and professional experience. So uh, it's okay. The AI note taker is confusing me, but that's okay. So so uh, so I've grown up in the U.S. since when I was in junior high school. My parents immigrated from India and went uh, through school in southeastern Pennsylvania outside Philly, and then went to Princeton for 8.5 years, did undergraduate and graduate work all the way through a PhD in mechanical aerospace engineering. And then I had a good productive day job career at Boeing, working in mostly in product development here in Boeing commercial airplanes. Worked at various times in Renton, Everett, and so on, and worked on the original 777, the 787, technology projects. I was the PD chief for advanced concepts for a while. So it was a productive and great career. I enjoyed it. I retired in 2020 from Boeing. Kind of separate and parallel from Boeing, I've been personally interested and quite passionate about renewable energy for a long, long time, meaning more than 30 years, and worked on stuff as a hobby and interest for a long time. But after I retired, I've been focused really full time on advancing renewable energy innovations and inventions. And that's kind of what I'd like to share with you folks today. Just a kind of a little motivation and then a summary of several of the things that our little nonprofit is trying to advance. Mostly right now with university collaborations. Actually, I have some stuff with UW, some I had stuff with Wazoo, with Columbia, um, and and with a few other universities. University of Tulsa is starting something now. So that's kind of my modus operandi. I'm going to share my screen um, and to the PowerPoint. Let's see, you see slideshow beginning. Okay. 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 So I think this will work. If we wind up not seeing something, I can move things around. So the title of my little spiel today is Rook Enterprises Disruptive Innovations in Renewable Energy. And I'm happy to have this opportunity to share some thoughts and data and innovations and insights. And to start with, just a little, let me see if I can move this thing off somewhere so it doesn't block everything. Okay. So renewable energy LCOEs have been steadily declining. And what an LCOE, and many of you probably know this, is a life cycle cost of energy. It's one of the standard metrics of how much does energy cost? What is the dollars per kilowatt hour or megawatt hour? And this one is in dollars per kilowatt hour. And the point of this chart is really that renewable energy, look particularly at that solar photovoltaic column in the middle and the um, uh, onshore wind columns. What it's saying is that prices from 2010 to 2021, due to advances in the technology and the innovations in both solar and wind, um, these types of energy are now cost competitive with fossil fuels, which is that gray band that starts in the left around zero point 0.1 plus or minus something and goes all the way left to right across the chart. And so what you're saying is, look, where in 2010 solar and wind to be competitively implemented as major producers of energy for the United States would need some government subsidy. Right now, they don't require any subsidy at all. They make their own business case. And what I'm going to be talking about is some innovations that can further reduce the cost per of renewable energy, make it even more cost competitive. So it's not like an argument of how much does the government need to subsidize. The government doesn't need to subsidize at all. We're already there, and going forward, um, on its own merits, renewable energy is going to be able to beat fossil fuels. Okay, so with that, the specific things, I'm going to go through a portfolio of 6 of our ideas, and some of them are relatively low risk or modest risk, and some are really deliberately audacious in scope. But I'm hoping that sharing this with you, you'll find it thought-provoking, and at least one of my philosophies where I am, I'm now a senior citizen. I really want to inspire the next generation, that's you folks, to think boldly. Don't ever let yourself feel that just because 90% of the people are working on making the next 2% improvement in something, that you should hem yourself into that kind of thinking. Think boldly, and you can do great things. Okay, so the first one is called Super Surya. It's a rooftop solar cogeneration system. The second one, the cost system or concentrating offshore solar system, is an offshore solar power system. The third one is kind of an interesting niche concept for Arctic communities. The fourth one is one of these super audacious concepts to actually capture wind energy while thickening ice in the Arctic and Antarctic to combat climate change. The fifth one is a wind energy system, and the last one is a ginormous energy storage system. And we'll get to reasons for each of these and kind of the thought process. So the very first one, then, the Super Surya or concentrating rooftop solar system. We got a patent for it. I'm an inventor, and so one of the things that I have the ability to do more than ordinary engineers is to be able to prepare and prosecute a patent myself. And so that's actually a cool skill. And so as an aside, I'll encourage all of you, any of you who have that inventive streak, try and teach yourself how to do that. There's a really good resource called Patent It Yourself, a book that can help you do that if you ever have a mind to do it. And I'm happy to help consult or encourage some of you to do that. Anyhow, the Super Surya, what's the idea? The basic idea is that solar panels, from the very first chart, we saw that they're already cost competitive. And they're very simple. They have no moving parts. They're very lightweight. They just mount on the roof of a house or a building. They can be integrated with buildings. The biggest challenge with solar panels is their efficiency is really quite low. So a simple silicon solar panel, even with monocrystalline silicon, is around 20% efficiency. So the sunlight comes in, radiation from the sun comes in at 1,000 watts per square meter all over the world when the clouds aren't blocking it on a nice sunny day like today in Seattle. So that energy of 1,000 watts, if you have a solar panel that's a square meter and pointing directly at the sun, where the energy coming in or the power coming in is 1,000 watts, it'll harvest 200 watts. And that's just a fact of life. So the motivation of this thing is with low concentration and cogeneration, can you increase that harvest from 20% all the way up to 60 or 70%? And how do you do that? So the idea is right now, what a solar panel does, if you ask yourself the question, the energy comes in, what happens to that 80% that you're not harvesting? The answer is it's waste heat at a temperature you can't use. So it'll warm up a little bit, but you can't use that heat. The idea of this thing is you're trading off a little bit of complexity. You have a device that has a parabolic reflector. So you're concentrating the sunlight. You have a tracking system that follows the sun. And this thing can still mount on a roof like a solar panel, but it will harvest 20% of the energy as photovoltaic electricity, and it'll harvest another 40 to 50% of the energy as usable heat with a heat transfer fluid going behind the solar panels. And the usable heat will be at something like 70 degrees centigrade, which you can use for domestic hot water when you integrate it with a home or a building. And you can use it for supplemental building heat or home heat. So that's the guts of the concept there. Just for the sake of time, I'm going to go through these fairly quickly. So the nominal the sizing of this is something like 1,200 watts of electricity and 27 or 2,800 watts of usable heat for a single module that fits on a roof. It can complement conventional solar panels on a roof. So if you have a house, for instance, which has a south-facing roof side and a north-facing roof side, the conventional solar panels will typically go on the south-facing roof side. This device can fit on the north-facing roof side, and because it has a tracking system, still has equal ability to harvest energy at full capability on the north side. And so it can complement and provide, allow homes to go from being kind of 50% solar dependent in the winter to really close to 100% by providing that heat element. So that's the idea. There's more stuff here. We can make this presentation available so you can look at it in more detail later. Let me move this over to this side. We have done some prototype testing, and sorry, I gotta go back. I have sorry. This will show my poor WebEx skills or Zoom skills. Anyhow, so there is a UW team actually currently working on this prototype on the top right. It's headed by an undergraduate student named Sanny Wan, and there's like 5 or 6 students in that team. They're going to complete the prototype, they're going to test it, and they're entering in 2 contests. One is the Energy Tech University Prize, and the other is the Dempsey Startup Competition. So any of you who are interested in knowing more about that, just contact Sanny, and if you want to get involved, certainly you're welcome to do that. And then in terms of markets, then I don't want to belabor this just for the sake of time, but there's significant markets for this all over the US as well as all over the world. And where people conventionally think of solar as, oh, it makes sense in Arizona, but it couldn't possibly make sense in Washington State. My counterpoint is even simple solar panels. One of the largest adopters is Germany, and they're far north of Washington State. And their insulation amount of solar energy they get is lower, and they still use it effectively. And so, especially with this low concentration, it's almost ideally applicable in places where you need some heating, and everybody needs domestic hot water. But if you need supplemental building heat in places with a cold but sunny winter, think Chicago, it's actually a really good fit. Okay, that's the end on that first concept. I do want to take just a quick pause at the end of each topic so that if people have questions, comments, critique, let's spend just a few minutes on that, and then we'll move on to the next one.
So how much is it estimated to cost for one of these rigs?
Oh, so that's a really good question, and I don't have a definitive answer. That my arm waving answer is going to be that we hope to get the LCOE competitive with conventional solar panels, but the output is something different, right? Because it's outputting both electricity and usable heat. So that's the simple-minded answer. It turns out it's not, since we're still in the prototype phase, it's really hard to get those numbers, and that's part of what Sanny's team is going to work on for their business content competition.
And just one other thing is, do you lose a lot of that thermal energy when it's like, cold outside or something in between transferring it from the super studio to the like house, for example?
Yeah, the answer is you don't lose a lot, and it is a really good question. The answer is it's a devil in the details kind of problem, but you need really good insulation on the heat transfer fluid coming from the roof of the house into the house. Um, for a while, a long time ago, one of the early set of solar systems in the U.S. was actually solar water heating and you using things. So there is technology on good insulated piping, and if you do it well designed and engineered, you don't lose a lot.
Very cool. Thank you.
Okay. If there's no other questions, Lynn, let's move on. So the next kind of broad category is this area called concentrating offshore solar systems or COS systems. And the the thought that I want to seed in you folks' minds is if you can go offshore, especially for utility scale solar, it's such a good idea because you're not you don't have the land costs. You don't have to compete for other land uses. Humankind we're a species that lives on land, and so we need land for homes. We need lands for farms. We need lands for nature, for forests and fields. And so one of the kind of quasi-legitimate objections to covering thousands of acres with solar plants is, well, you could have used that land for something different or maybe better. So the broad answer is, well, why not? Solar is equally available over water as over land. Why not do it? So again, it's a devil in the details problem because water, first of all, you got to get the system somehow on something that's floating on the water. So that's more expensive. Um, Truth be told, right now, there are starting to be commercial installations of offshore solar, which use just really simple floats with really simple solar panels mounted on them. So nothing magic from a technology point of view. And they're getting implemented on places like reservoirs. Um, but I'm thinking kind of in a grander way. And so if you look at the offshore solar resource within all the EEZ, and EEZ is the exclusive economic zone of a country, it's way more than enough to meet 100% of all of humankind's energy needs. Just with offshore solar, you need zero wind, you need zero onshore solar. If you could figure out a way to get offshore solar LCOE low enough. Okay. So the concept here is to basically have, if you look down from the sky, you have a system that looks like a big circular floating array. And you have at least one axis tracking of the sun by anchoring this using tethers to the floor of the lake or the reservoir or the open sea eventually, and using that to track the sun. And then you use something really like the Super Surya technology with low concentration. And so again, you can get electricity, you can get usable heat, or you can take some of that usable heat and run something called an organic Rankine thermodynamic system to get more electricity instead of heat. So those are all the things you could do. And there's also kind of spiral developments of these where you use it for um, um, what's called district heating. District heating is a technology that's actually implemented on quite a large commercial scale in Europe. In the US, it's really small. But the idea, again, is if you have this low grade heat at like 70 degrees temperature C heat transfer fluid, you can use it to heat buildings on the shore. And so those are all the ideas of this thing. Um, I currently have a student at the University of Tulsa doing a capstone project on this cost system, and we'll develop more data on the costs, the value propositions, the technical risks. And it's the system is also kind of cool in that the basic concept is very scalable. You can have a really small system like this mini scale system and use it for small waterfront property owners or ranches or farms. And then you can go all the way to this 25 megawatt electric system, which can be used to power a coastal city or can be out in the open ocean. And I'll be the first to say there's a bunch of technical, as soon as you go into the open ocean, there's a lot of technical issues in dealing with just the waves and the storms. Um, One kind of application I thought of that would make a lot of sense is San Francisco Bay. You could implement these in a place like San Francisco Bay, and um, my rough calculations say you can use 2% of the Bay water area to provide all the energy needed for the Bay Area. And I also did a little kind of thought experiment on really large scale. If you ask yourself the question, where in the United States is the sun the strongest? It turns out the US actually owns a couple of teeny tiny islands out in the middle of the Pacific Ocean on the equator. One is called Jarvis Island and one's called Howland and Baker. And because the EEZ goes 200 miles out from each of these islands, there's actually a tremendous amount of area there. So in the long term, and that area right near the equator is also um, because it's called the doldrum area for meteorologic reasons, it doesn't have hurricanes or cyclones or typhoons. And so that's almost a perfect place for, in the long term, generating green hydrogen using solar power and these kind of systems. Okay, so I've kind of blathered on about the motivation of concentrating offshore solar. Thoughts, questions on that?
So I
Just
guess
wondering. Oh, you can go on.
go ahead, Maddie.
Um, like how durable would this be? It's like obviously in the ocean and salt
Yeah.
water, but also just like how much are we like how often would things have to be replaced or repaired?
It's a super good question. And so the answer really, when I'm going to go back to this mega scale system and talk about something fundamentally, I think the answer to your question, Maddie, is you have to design in and engineer in a very robust floating platform that can deal with the foreseen wind and wave conditions. So the wind energy business has already figured out how to do this mostly with their offshore wind turbines, and they're very massive devices. They have rotors that are a couple of 100 feet in diameter, and the foundations for that these devices that are out mounted out in the North Sea in commercial operation off of the UK and Norway, they survive really harsh conditions. So it's a matter of good engineering for waves and winds, and clever siting to not locate it where you're going to have, you know, yearly hurricanes. You don't want it there. But that said, basically the floating platform, well, my guess is it can be a steel structure like a big barge, but it can also use things more clever, like there's material systems that are used in pipes that can float, and you just have to build it big enough. And there is an advantage of scale. The bigger the floating structure, the smaller the wave is relative to the structure. So in some sense, if you can build a device that's at this really big scale with a bunch of, think of it as floating pylons or floating pilings. Um, think of the other analogy I would give you is oil rigs in the Gulf of Mexico. Industry has proven that you can build a robust enough floating oil rig that it can survive most hurricanes.
Cool, thank you.
Okay.
I guess this isn't quite a question, but I think this has a lot of merit, especially in like an aquaculture setting. So people that are already like using
Sure.
kind of a lot of sea area, and they might not be able to fit for like, wildlife or like stock fish health reasons, things that close together.
Yeah.
But I mean, putting this in between there would be like huge for people running aquaculture.
Sure, a really interesting thought. I hadn't actually thought of that one. There's a lot of synergies. There's also synergies like if you have these offshore from Southern California, they're having all kinds of problems with fresh water. So one of the easy things you can do when you have that usable heat at 70, 80 degrees C is use it to run a thermal desalination system. And so you can actually use these systems to offshore to convert seawater into drinking water. And places like Arabia could certainly use that feature in a really large extent.
Very cool. Thank you.
All right. Okay. So we're going to move on to, and I'm going to try and pick up the pace a little just because I got a few more things to cover. So this one is like the Super Surya, it's a relatively smaller scale system um, to meet kind of a niche market in the Arctic. And it turns out I visited both Barrow in Alaska and Cambridge Bay in Nunavut in Canada. Turns out that the people over there, and I feel really sorry for them because you all winter there's no way to get there other than by airplane. And so and also it is unbelievably cold in the winter. And so it turns out their dominant energy need is for just heating their homes and buildings all winter. And the way they do it today, you guys won't believe it, but they take huge barges full of oil, barrels and barrels of oil. They take it in the summer, they stockpile the barrels of oil, and they burn it all winter. And the effective price of the oil for them is like triple what it is for us down in the mainland. And so, and these aren't rich people. So it's really a travesty. It's dirty and it's very expensive. So how do you solve this? It turns out they have ample wind, but the efforts to put conventional wind turbines there have by and large failed because they also have permafrost in the ground, and so you can't put a foundation into the ground. So that's the motivation. And the solution I came up with, and we got a patent for, is using something called an ice boat. You guys can actually, I don't want to spend the time here, but you can actually just do a Google search on ice boats and see some really cool YouTube videos. It's a proven technology. It's used recreationally. People ride these things to race in places like near Detroit. And even if the wind is blowing at 20 miles per hour, these ice boats move at 60 miles per hour over the ice. And so the idea is then, what if you take a bunch of these ice boats, a bunch of these wings, and put them in a ring and make the ice boats go round and around a ring and run a bunch of generators? Simple concept. We got the patent on it. I've been trying real hard to find a way to advance this. Did a project on this with some students from Wazoo. We actually they built a prototype. We tested it actually in a ice arena in Everett. So the concept, there's nothing magic about the concept. The concept works. Again, the devil's in the details on the economics. And I okay, as the parent of this invention, it seems to me real clear to me that it's the best solution for these guys. May not be clear to everyone, but we'll see where it advances and we find an avenue to commercialization. This is kind of like what it'll look like in an operational system. You have a bunch of these wings that go round and around the circle. There is a little bit of technical trickery because you have to control. I'm an airplane guy, so to me it's not hard. You control the angle of attack of each of those wings as it goes around the circuit in an active control way to maximize the power harvest from the wind. Any comments, questions about this one?
So they're on like a rail system?
No, they're all mounted to this ring, and the ring has skates or skis under it.
Okay, I see.
So the whole system just sits on the ice and rotates. It's like a bunch of ice skaters going in a circle.
Got it.
Are there any requirements for how thick or how long lasting the ice needs to be before they're safe to operate? Or
Oh, yeah, you bet. So the ice does have to be, certainly a valid point. The ice has to be a couple of feet thick. And in these villages in the Arctic, it's way more than that for 6 months of the year. Um, but it does beg the question, what happens in the summer? And broadly speaking, my concept on that is that those rings also wind up floating on that ice rink basically becomes a pond in the summer. And the system will still work in the summer, but the drag of those floats in the water is way more than the ice. And so it will produce a lot less power in the summer, which curiously enough, they need a lot less power in the summer because that their dominant energy need is heating. Well, that's a really good question.
How does snow affect its function?
Oh, that's a good question too, Maddie. And so the idea would be that um, there's some cleverness in the runner design so that it works as a skate when there's ice, and when there's a lot of snow on the surface, it'll work as a ski basically. So you got to kind of effectively design that runner so you don't wind up having to clear the snow if there's snow. All right. And we've done some market analysis in Nunavut and so on. I'm going to skip through that. Um, we're trying to find some small manufacturer or startup company who might be interested in trying to develop and commercialize this. And and for what it's worth, if a bunch of students want to put together a company and take a shot at developing it, let me know, and we'll work with you guys. Okay. So there's a developed version of this, and this one I'm going to go through a little quickly, but I want to at least share this concept because it's an audacious concept for what I think is an important problem. And this is the same wind energy system, but at a larger scale and out in the sea ice in the Arctic Ocean and on ice shelves in the Antarctic. And it's called ISTRIS or ice sheet thickening renewable energy system. So it harvests the wind energy, probably to make green hydrogen. But while it's harvesting wind energy, what this system does, it's on a floating sheet of ice in the Arctic or the Antarctic. It uses some of that energy in the winter to pump water from under the floating ice and either drip it like a drip irrigation system or spray it like a snowmaker in a ski area on the surface. And the idea is you keep running this thing every winter and you'll wind up actually thickening sea ice or thickening ice shelves while getting renewable energy. And to me, that's a win-win proposition. This is kind of the idea is you have a whole array of these things and build a beam of thickened sea ice or thickened ice shelf. That's a basic concept. And what's the value? Well, you harvest the wind, you thicken the ice to combat climate change, which is melting sea ice in the Arctic, and it is also melting the ice shelves in the Antarctic. So it's a nature-based solution. And so I really am pretty jazzed about this. I was excited about this problem, and this is not to be overly dramatic, but I do want to share this little quiz question that I heard many years ago. It was probably 2 decades ago by a gentleman named Dennis Bushnell, who at that time was chief scientist at NASA Langley. And he was giving this presentation at a conference. This was long before climate change became an in thing or a hot topic for that the whole world is discussing. But Dennis was ahead of his time, and he was very much a visionary. And so he asked us a quiz question. He asked the audience. He said, "Well, IPCC 4 experts said that for climate change scenarios, and this was 20 years ago, this if the world's temperature rises 2 to 4 degrees C, the sea level can rise zero point 0.2 to zero point 0.6 meters by the year 2099. That was their forecast then. It's worse now. So he said, now you smart scientists and engineers in the audience, suppose the actual temperature rise is a lot worse than the 2 to 4 degrees C. Suppose it was 6 to 10 degrees C. How much do you think the sea level would rise? So that was his quiz question. Any if you want to take a shot, if you don't already know the answer to this.
I'm gonna guess it's more than like 6 to 12 or 1.2 meters.
More
Just
than one
based
point,
on
more than 1.2 meters. Yeah, and the whole purpose why Dennis asked us this question is his point was the scientific and engineering community does a really good job of talking about nominal predictions, but they're really gun shy about saying how bad things can get. And the answer, which floored me at that time, and should floor you guys if you haven't heard of this before, is 75 meters. And and the reason the answer is 75 meters is there's a ginormous nonlinearity in the system where if the temperature goes up 6 or 7 or 8 degrees centigrade, all of the ice in Antarctica and Greenland melts. And if you take, and so Dennis challenged us to do this. I could tell you guys 20 years ago when I first heard this, I was incensed. I was an engineer. I was proud of my engineering capabilities. And I said, you can't possibly be right, Dennis. I went home. I did the calculation myself. Any one of you can do the calculation yourself with a simple calculator. Take the volume of ice in Antarctica and Greenland, convert it from ice to water, liquid water, distribute it over the seas of the world, the area of the total ocean of the world. And so you're just taking volume divided by area, and you'll get the height increase. And believe it or not, it's 75 meters. Well, somewhere between 70 and 75 meters. 1/3 of humankind goes underwater. Why is that? Because humankind have built all our cities along coasts, right? So New York, Miami, all of Florida, LA, Seattle, we're all underwater, folks. And so Dennis's point was this issue, the climate change folks, they're already viewed as kind of being doomsayers. But quite honestly, from what Dennis told us, they're not articulating the doom nearly as bad as it could be. It could be terrible. Quite honestly, the doom from the melting of Antarctica and Greenland is truly a human catastrophe and an environmental catastrophe. If you try to dollarize it, it's 1/3 of world GDP or $30 trillion a year. And so the point is, can't let it happen. And that's why it's great that there's activity going on trying to get the nations of the world to get their act together on cutting carbon emissions. But if they don't cut the carbon emissions, then this kind of nature-based solution where you actually thicken the sea ice and ice shelves may be the saving grace that allows you to thicken sea ice around the ice shelves in Antarctica, and so to speak, sequester sea level back into ice. Okay, any comments on this? Questions? Don't feel shy if you want to call me crazy. I'm okay.
So the mechanism of thickening it is just by making it mist, so it's easier to freeze it back to ice.
Okay, so maybe I wasn't quite so clear on how the mechanism works. So the mechanism is as simple as in the winter. What happens is in the winter, think of any one of these ice shelves. So let's assume that you're standing at the edge of the Ron ice shelf in the Antarctic winter. The temperature of the temperature just under that ice shelf is exactly 0 degrees centigrade, because you're at the phase change interface for liquid water to frozen water. The air temperature immediately above the surface of the ice is minus 30 centigrade. And so all you have to do with the system is you're harvesting wind energy. You're using a fraction of that wind energy you're harvesting to take a simple pump that pumps water from under the ice shelf, which is at 0 degrees C. And imagine just like a drip irrigation system. You just drip it into the air outside. It'll immediately freeze once you drip it.
Okay,
And
that
it's
makes
as
a lot
simple
of
as
sense.
it's as simple as that. And basically what you're doing is all through the winter, think also, some of you may be skiers. You've seen snowmaking machines in ski areas, and they basically use something like that principle. They take water from a pond. When there isn't enough natural snow, they pump it at pressure into the air, it freezes and makes snow. And so basically you're all through the winter, you'll be taking some of that water and making it ice or snow. And then over the summer, yeah, some of it's going to melt off again, but you're basically combating the natural process where um, right now the summer melt far exceeds the winter thickening.
That's really cool. I didn't even, yeah, that's my comment. Yes.
Okay, thank you. I appreciate it. All right. Um, okay, I think we're doing okay on time. Then the next one is called the revolving overhead windmill system. It's very similar to that revolving ice boat system, but this is just intended to say wind, like solar, there's enough wind in the world, offshore wind, to meet 100% of foreseen human needs. And like the revolving ice boat system, the idea is to use these vertical wings or sails to harvest that wind by making it go in a circle. And so it's very similar to that, but the idea is, instead of the conventional offshore wind turbine, um, I think this is a better solution. And I'm currently mentoring a UW senior, Arjun Subramanian, who doing some modeling in CAD and FEA and stuff to kind of flesh out the concept. We're going to present this at a conference of the American Society of Mechanical Engineers this summer. So this is kind of an architecture for offshore wind that in my mind will have a lower LCOE than current offshore wind turbines, and has some other advantages also, like lower risk to seabirds and marine life, lower noise, and the ability to scale up to a larger scale.
So I might be out of my area of expertise here, but I've seen like, helical wind turbines that are
Mm,
standing. They'll use a helix, so any direction
yes,
of wind that you hit it at, it will spin.
yes,
What's
yes.
the advantage of something like this versus like an array of helical turbines?
Yeah, so that's a really good question. So the helical turbines are also vertical axis wind turbines. The difference from that is, if I go to this thing, here you have a bunch of wings that are going in a circle. They're all going in a circle around the circle on basically a floating truss that's sitting in the sea. The helical wind turbines, that you can't build them at this scale. So the way you would do that is you'd have a bunch of individual floating platforms, and so where you have each of these wings, you can replace it with a helical wind turbine. Um, I think your question is a good one, and ultimately the detailed engineering design and analysis will prove out which might be the better solution from an LCOE point of view. So I don't want to throw any darts at the helical wind turbine guys, but basically there's a much smaller scale device. And so the way to ask your question is, if I replace each of these wings with a helical wind turbine, would I be ahead or behind from a cost point of view? And to be honest, I don't know the answer to that. All right. Let's see. Let's go on. And I think we've already talked about the value propositions in this and where we're going. Okay. Sixth and last one is arguably my most audacious idea, and and I hope if you take one thing away from this is be bold in your thinking. Don't think your ideas are stupid. All ideas have to go through a long maturation process, and you have to be able and willing to receive critique and what do you do about this problem, and just methodically work through it. But be bold in your ideas and explore them. So this one has to do with energy storage. And I'd like to introduce that subject by saying, why do you need energy storage? Fundamentally, if we're going to go from an economy that basically burns fossil fuels to provide energy, electricity, say, to something that depends on solar and wind, the problem is both solar and wind are pretty intermittent. So for solar, for instance, we know we have it in the day, we don't have it at night. So if consumers need electricity at night. In a modern society, so you need to store that energy from the day to the night on the solar. Similarly, in wind, some days you have a lot of wind, some days the wind is pretty idle, and so you're not generating. Again, you need storage. So it turns out there's this clever scheme. I'll get back to this first chart, which kind of says everything together. But the motivation is how much energy do you need to store? Back when we had the last administration, which had this very ambitious target of 100% carbon pollution-free electricity by 2035. The current administration certainly would not support that. But whatever the timescale is, if you do the thought experiment on if we ever get to 100% carbon pollution-free electricity, how much storage do you need? The National Renewable Energy Lab, or NREL, did a study on this, and the answer is a pretty broad range, but the numbers are really mind-boggling. So they kind of say for diurnal storage, you need to add somewhere between 120 and 350 gigawatts of storage, and for long duration between 100 and 680 gigawatts for they studied several different scenarios. So the total medium to long duration storage is in the range of 220 to 1,030 gigawatts. Keep in mind, what's a gigawatt? 1,000 kilowatts is a megawatt. 1,000 megawatts is 1 gigawatt. So it's a lot of power. A gigawatt is 1 billion watts. Okay. So when you say you want to go to a large amount of renewable energy storage, what are your options? So it turns out a lot of people don't realize that the world's current largest amount of energy storage is actually using pumped hydro. And pumped hydro is a real simple system. You have water at a certain level, you pump it up to a higher level when you have excess power in the grid. When you need power, like power at night and the sun isn't shining, you run the water from the upper water reservoir to the lower through a set of turbines, generate electricity, and voila, you have your energy storage. It turns out that pumped hydro currently provides 94% of global energy storage. And a lot of people don't realize this. There's armies of people working on better batteries, and there's a smaller army of people working on hydrogen as a storage for energy. And I'm not going to throw rocks at anybody, but each of these has pros and cons. But pumped storage has the advantage of being super simple, not needing toxic materials, and really being able to store very large amounts of energy. The little batteries that you have in things like your smartphone, I would be the first person to say, yeah, an energy efficient battery is the best solution for this. But when you say I need to store gigawatts of power, then you need something different. So what is this concept? And the concept itself is super simple. It turns out that the biggest objection to pumped hydro is typically for any new hydro installation, you have to build a dam, you have to dam a river, you're going to flood a large area, you're going to cover several hundreds of acres are going to go from land to being underwater. And so the environmental impact is very large. And so that's one of the biggest reasons why you don't have new pump hydro projects happening in the US. They're still happening in other parts of the world, in China and India and other places in the world. Lots of hydro projects still going on. So here in the US and Canada, it's almost like there's an amazing God-given thing where you have two bodies of water, Lake Erie and Lake Ontario, that are separated with 99 meters of vertical elevation, with Niagara Falls in between. And so this was my aha moment, which happened a few years ago. And I said, wowie zowie, to meet those kind of enormous energy storage needs, why don't we find a way to take some water from Lake Ontario when we have excess power, pump it up to Lake Erie, and then at night, when the wind isn't blowing, run it the other way through a bunch of turbines. And then I've actually done a bunch of work on this. I mentored a project at Columbia University where the students did quite a bit of work on it. We presented at an international conference in Windsor, Ontario last year. And so I have pretty high confidence in these numbers. Now, there's no doubt there's all kinds of people who will have all kinds of objections to the scheme. But in the big scheme of things, this single system can provide about 400 gigawatts of power and power storage, or about half of the total energy storage needed for that 100% green electric grid scenario. And what's amazing is just because of the size of Lake Ontario and Lake Erie, the water level that goes up and down between the two lakes, you only need 1.3 feet of water levels change in Lake Ontario and 1.3 feet in Lake Erie for this thing. And so as you pump back and forth, and then part of the reason I got a good patent on this, I got US and Canadian patents, is you need some cleverness to manage the flow over Niagara Falls so it stays where you want it, even though you're messing with the water levels of the two lakes. And so there's some cleverness there, but it's an easily technically solvable problem. So this is, I think, a kind of, it's definitely an audacious proposal, but it would allow you to meet half of the U.S. energy needs. The world's largest pump storage system now is in China, and this would be 100 times bigger than that. And in my mind, it would boost the economy. You don't have to condemn a bunch of land. Does it have issues? Of course it does. One of the biggest technical issues is how do you build that giant water pipeline that connects the lakes underground? So it would be the largest tunneling project in human history. Can it be done? We've talked to some companies that have innovative mining tunneling approaches. So, but it's overall a concept way out of the box, but why not? All right, I think I'm done. So sorry for a little bit of a fire hose, but I hope you guys at least find it thought-provoking and interesting, and also encourage you to think out of the box on solutions to all kinds of, we humankind face all kinds of problems. And when you look at things from a historical perspective, I'll tell you, having worked in aerospace for many years, if you look at the difference between where the Wright brothers were with their airplane and where a 747 flying today, in less than 100 years, the technology change and the solution change is totally mind-numbing. And so each of us can be the architect of the future, and we should try. All right.
Yeah, Mithra, I think I can speak for all of us, but that's super interesting and inspiring to see these new things that like nobody's talking about, changing renewable energy at a large scale. People want to go for like conventional solar and wind, but this is really cool to see.
Yeah, and I think you'll find for all of you, I don't know what all fields you're in, but almost agnostic to the field you're in, what you'll find when you go into your careers is most big companies, Boeing is an example, and almost in every industry, they will spend 90% of their resources on small evolutionary improvements. And from a business case point of view, you can't really fault them for doing that. But for those of us who are kind of visionaries or disruptive innovation people, we work in that bottom 10% or the bottom, some cases, the bottom 1% of out of the box ideas. And you have to be prepared for the fact that many of those out of the box ideas will bite the dust for various reasons. It may be technical, economic, regulatory, whatever. But the good news is, if you look at it from a historical perspective, it's always the disruptive innovations that make the step change improvements in human civilization.
Totally agree. Yeah, that was very cool. If anyone else has questions,
I was just gonna say thank you.
Oh, you're very welcome.
yeah. All right. Thanks so much for taking time out of your day. Like, I know
Sure.
you're busy. But I definitely appreciated hearing this, and we'll post it to our uh for the rest of our members so
Wonderful.
they can see. But
Okay, and
yeah,
and maybe just to get off the stage, I would say if any of you have further interest or questions or something, it's okay to share my email, and people can shoot me a note to share a thought, a question, an observation, or even an idea. It's all I'm at that phase of my life. I like to work with students and to inspire the next generation.
perfect. All
All
right.
right. Thank
Thanks
you
so
all.
much.
Have a good evening.
Yeah, you too. Bye bye.
Bye.